fates will not all be the same. This star, the same size as our own Sun, will fade to a hot but stable white dwarf star, barely visible to Earth's telescopes. And this one will erupt into a fiery supernova and then collapse into a hot, dense neutron star. But a very few of these stars, the very massive ones, will end their days as some of the strangest objects in the universe. Objects so massive yet so compact that they trap light itself behind a dark veil.
A star is really a violent competition between nuclear physics, generating all of the heat and power that makes them shine, and gravitational physics, which wants to compress them all to a point. Now, nuclear physics holds gravity at bay, in some cases for billions of years. For the Sun, fusing hydrogen into helium will keep it supported for 10 billion years. But for a star that's 30 times as massive as the Sun, after only 1 million years, the nuclear fuel has run out.
And in fact, it's kind of a funny thing. There's this what people call onion layer process, that in the middle you have the highest temperature, so you have the most energetic fusions happening at the center. You might be making iron in the middle, but then you're fusing helium farther out, or fusing maybe oxygen and carbon farther out.
Once iron dominates the central core, the star can no longer generate the energy needed to counter gravity, and the central core collapses, radiating a burst of energy outward that signals a much bigger cataclysm about to unfold.
As it compresses down, it gets smaller and smaller, gravity's getting stronger and stronger, and there's nothing left to stop it. It's going to form either a protoneutron star at the center, or in some cases, for very massive stars, directly into a black hole. Now, the key is, for observational consequences, the rest of the star doesn't know about this yet. And the rest of the star starts collapsing down on this missing core, this missing floor. If it forms a protoneutron star, the rest of the star suddenly stops and bounces. It goes flying out. And the difference in the size between the original core and the final protoneutron star is so extreme that bounce has a huge amount of energy. Much more energy than is required to completely blow the star apart. And we have a name for that. Those are supernovae.
Most of the star is thrown off into space, yet a remnant of the star remains at the core. If what's left is less than about 3 solar masses, it will form a neutron star. But if it is more than 3 solar masses, no force that we know will stop it from collapsing into a dimensionless point called a singularity. That is the massive compact heart of a black hole. But what is a singularity?
Yeah, so I guess at some level, maybe this is collapsing to a singularity is not a logical conclusion at all, because there is no logic to singularity. Singularity is the point at which, at least none of the laws of physics, as far as we know, applies. And I think most physicists think there's a theory that we still don't know, the theory of quantum gravity, in which you have a consistent description of both quantum effects and gravitational effects. Such a theory is missing right now. But if you have that, then that's going to replace this idea of singularity, which really doesn't make any sense.
Eventually it means that something like a space-time point doesn't exist, because you cannot really distinguish between arbitrary near space-time points. And that's what quantum gravity is mostly about. It's actually explaining something, what is space-time and what is quantum space-time. And the problem is really to build up a model that delivers basically an answer to what is quantum space-time, but which also connects to all the other stuff we know about the universe.
We don't know what happens there. I can't tell you what that is. But on the other hand, in some sense, a black hole is more than that singularity. It's the set of interactions, the set of dynamics that's going to happen to everything around it as a consequence of that singularity. It's the gravitational field, or the space-time, that's left behind by this collapse.
To see how a black hole reveals itself through its gravity, we'll travel to an established black hole that orbits in a binary system with a blue giant star. The first thing we notice is how star stuff is being pulled, or accreted, from the surface of the star by the tidal forces generated by the nearby black hole. If we follow the accretion trail, it will lead directly to the black hole.
To a physicist, this is all the black hole is. If I'm an astronomer, I never see that. And we see a lot of things that we think are black holes. And the reason why we see them is we don't see black holes all by themselves. We see black holes in the middle of stuff, lots of stuff. And it's the interaction of the black hole with that stuff that produces all of the observable signatures that we can go after. Stuff orbits around black holes very similarly to stuff orbiting around the sun. And if I'm far enough away, I really couldn't tell the difference between a black hole that had the mass of the sun and a star that had the mass of the sun. But that black hole is much, much more compact. And so as stuff falls down, it accelerates and it gains energy as it falls. And this stuff that's falling in towards the black hole is accelerating and gaining energy, turning that energy into random motions, which then ends up shining, heats up the accretion flow, and it shines. Okay? So all this gas rushing headlong in this traffic jam to get in towards the black hole as it spirals in, rubbing up against each other, liberating all of this gravitational potential energy as it falls in, ends up shining brighter than galaxies in some cases.
At a certain distance from the center, there is a zone of complete darkness, an area where the effect of gravity is curving space-time so much that nothing, not even light, can escape. Like trying to swim against a current that is carrying you faster and faster towards a waterfall, there is a distinct point where the current is so strong that the swimmer can no longer make any progress upstream. In the same way, light that travels too close to a black hole will become trapped, unable to escape because space is falling inward faster than the speed of light. This edge of darkness is called the event horizon, and it gives the black hole its name.
For the black hole, once you cross the horizon, there's no going out. Everything goes in. That's why we call them black holes. The other way we see black holes is through outflows. And that sounds a little counterintuitive. How does a black hole push anything going out? After all, it's a horizon. It's characterized by stuff going in and not coming back. Well, it's that spin. It's the fact that the black hole goes around. And if I create a bunch of gas, and that gas has magnetic fields in it, those magnetic fields feel the influence of the rotation of the black hole. They're dragging those field lines around, and they spiral them up, and matter accelerates out along this cylindrical or nearly conical, in some cases, field line structure. And we call those jets.
So jets are basically elongated plumes of gas or plasma that seem to be moving at relativistic, very, very fast speeds close to the speed of light, and basically being ejected from where we think a black hole is sitting.
So far, we have been describing stellar black holes formed by the death of the most massive stars. In fact, you are looking at one of the most famous, named Cygnus X1. Yet, stellar black holes are so compact that they are very difficult to observe from Earth. Luckily, astrophysicists have discovered another type of black hole. These are called supermassive black holes, and they are millions of times larger than their stellar cousins. They are found in the center of most galaxies, revealing themselves by way of their immense gravity. These balls of light show the movement of stars near the very center of our own galaxy. Each is traveling in an orbit around the same invisible mass. These orbits betray the presence of a supermassive black hole over 4 million times the mass of our Sun. We don't know precisely how they are formed, yet they are our best chance of observing black holes directly and solving the mysteries about one of the universe's strangest objects.